DSpark, confidence-scheduled speculative decoding with semi-autoregressive generation by the teams at DeepSeek AI and Peking University. Welcome to AI Paperslop, the YouTube series where we summarize AI and tech papers for technical folks like you so you can stay right up to date. Let's just dive right in.
Yeah, let's do it.
So if you run large language models in production, you know about speculative decoding, right? It speeds things up by having a smaller, fast draft model propose tokens, which your massive target model then verifies all at once.
Right, but there's a huge problem. Parallel drafters generate tokens incredibly fast, but they lose accuracy super quickly. It's this thing called suffix decay.
Exactly, and verifying those long, inaccurate drafts in a high concurrency production system, it just wastes precious GPU batch capacity.
Yeah, it completely tanks throughput. But DSpark solves this with a two-part framework. First, a semi-autoregressive drafter that basically combines the speed of parallel generation with the coherence of sequential modeling.
Wow.
And second, a hardware-aware confidence scheduler. It dynamically trims those draft lengths based on real-time server load. The result is like 60% to 85% faster generation speeds per user at matched throughput on live DeepSeek v4 production traffic.
That is massive.
Yeah.
And they didn't just, write a paper about it. They actually open sourced the DSpark checkpoints and the DeepSpec training repository for the community.
Yeah, you can literally go grab it right now.
So before we look at DSpark's actual solution, we have to understand the specific bottleneck in current speculative decoding architectures that force this innovation.
Right, because there's this really brutal trade-off between the two existing types of drafters. It's basically autoregressive coherence versus parallel speed.
Okay, let's unpack this, because if you look at autoregressive drafters like, say, Eagle 3, they are highly accurate, but their latency scales linearly with block size, right? It's an O of gamma situation.
Exactly. You want a 16-token draft, you pay for 16 sequential steps. So you're forced to use these really tiny parameter-light models to compensate.
Which brings us to the other side. Parallel drafters like DFlash. They predict all tokens in a single forward pass. So latency is basically independent of block size. It's an O of 1 latency.
Yeah, but that speed comes with a massive catch. Because they predict independently, they suffer from a huge drop in acceptance rates after the very first token. Position 2 has no idea what position 1 just generated.
Right. And the paper actually cites the position-wise conditional acceptance data on the Quinn 3.4b model.
Oh yeah, the MathPask data. DFlash hits this really high 0.88 conditional acceptance on position 1, but then it decays so fast because of that independent prediction.
Whereas Eagle 3 starts lower at like 0.81, but it actually climbs to 0.85 by position 6, simply because it conditions on previous tokens.
Right.
So think of it like this. Autoregressive drafting is like a slow relay race where the baton is passed perfectly. But parallel drafting is like a sprint where all the runners are blindfolded.
I love that analogy.
They start super fast, but eventually they just crash into each other. The paper actually calls these multimodal collisions, like trying to say, of course, or no problem, and the parallel drafter outputs the totally incoherent of problem.
Right, and of problem is guaranteed to be rejected, so you just wasted all that compute. But since both pure parallel and pure autoregressive models have these fatal flaws, DSpark basically elegantly fuses them together to eliminate those multimodal collisions.
The semi-autoregressive hack.
Exactly. Stage 1 of their drafting phase is the parallel backbone based on DFlash, which does the heavy lifting in one pass to generate base logits.
Okay, so that gets you the raw speed.
Yep. Then comes stage 2, which is this really lightweight sequential stage that injects transition information. They use a Markov head, which applies a low-rank transition bias. I think the rank is just 256.
Wait. If we add a sequential loop back into a parallel drafter, doesn't that, defeat the entire O of 1 latency advantage that made parallel drafters appealing in the first place?
You would think so, right. But the latency numbers in the paper are actually wild. The sequential Markov head is so computationally cheap that scaling the draft length from 4 all the way to 16 adds a microscopic 0.2% to 1.3% latency overhead.
Oh, wow. So it's practically free.
Basically, yeah. And it boosts the accepted length by up to 30%. They even found that a shallow 2-layer DSpark outperforms a deeper 5-layer DFlash baseline.
Because that tiny injection of autoregression is just vastly more parameter efficient than simply stacking deeper parallel layers.
Exactly. So now DSpark can generate these long, high-quality drafts for almost zero extra latency. But then we had the second major problem: why generating 16 great draft tokens can actually hurt a production system.
Right, because we have to shift focus from the model architecture to the actual system-level operations.
Yeah, because the optimal verification length varies drastically based on the data domain and the current engine load. Like, structured tasks like code naturally sustain much higher acceptance rates than open-ended chat.
Sure, chat is way more unpredictable.
And under light server load, verifying 16 tokens is free. But under heavy load, verifying low probability suffix tokens occupies critical batch capacity that could have served other users.
Yeah, they cite this static threshold sweep diagnostic that proves this. For chat workloads, raising the confidence threshold filters out those rejected tokens and skyrockets the acceptance rate from 45.7% to 95.7%.
If we connect this to the bigger picture, while a static threshold works perfectly in an offline vacuum, a real production system needs to dynamically trim drafts based on real-time server traffic.
Which brings us to the second half of DSpark, the hardware-aware prefix scheduler, which acts as the system's air traffic controller.
Right, so DSpark predicts if a token will survive using a confidence head. But there's a catch. Raw neural network confidence scores are famously overconfident.
Yeah, the expected calibration error, ECE, is usually like 3% to 8%, right?
Exactly. So DSpark uses sequential temperature scaling, or STS, to calibrate these probabilities, dropping the ECE down to around 1%.
That's a huge improvement.
Yeah. Once it's calibrated, they use algorithm 1, which greedily sorts the valid prefix expansions and evaluates expected throughput against a pre-profiled hardware capacity curve. This is measured in steps per second, or SPS.
Okay, but hold on. I see a theoretical flaw here. If the scheduler looks ahead at the confidence the second or third token to decide whether to admit the first token, doesn't that violate the strict causal, non-anticipating property required to make speculative decoding mathematically lossless?
That's a really good point.
Aren't we introducing selection bias?
It's a brilliant catch, but they thought of that. They implemented an early stopping mechanism. The algorithm strictly halts the greedy search the exact millisecond the expected throughput drops.
Oh, I see.
Yeah, so ensuring the admission decision for step K relies only on the prefix up to that exact step perfectly preserves the target distribution.
Okay, so the theory is flawless, but theory often breaks in production. How did the DeepSeek team actually get this to run on live user traffic without just totally stalling the GPUs?
This is where the system-level optimizations for DeepSeek v4 come in. There's a huge clash between algorithm 1 and continuous CUDA graph replay. It's called zero overhead scheduling, or ZOS.
Right, because ZOS requires knowing the next step's batch size before the current step finishes.
Exactly. So synchronous scheduling would just stall the whole pipeline.
So how did they fix it?
With a brilliant asynchronous hack. The scheduler approximates the upcoming verification capacity using confidence head outputs from 2 steps prior.
Wait, 2 steps prior? Here's where it gets really interesting. It's like a time travel adaptation.
Yeah, basically. It forms a causal barrier, completely hiding scheduling latency while navigating those jagged hardware capacity cliffs. Oh, and I should mention the training optimization, too.
Yeah, what do they do there?
They used anchor-bounded sequence packing and cached forward pass activations, so they only communicate O of D hidden states across workers instead of full vocabulary logits.
That saves a massive amount of bandwidth. And it's amazing how they decouple physical execution from logical sequence tracking by flattening variable length queries into a 1D tensor using a marker tensor in sparse attention.
It's just incredibly clever engineering all around, and all of this intense architecture and asynchronous engineering culminates in the actual performance metrics. What happens when you point live user traffic at DSpark?
Well, starting briefly with the offline benchmarks, DSpark improves macro average accepted length over Eagle 3 by up to 30.9%.
Wow.
And over DFlash by up to 18.4% on Qwen 3 models. But the live deployment against DeepSeek's MTP1 baseline is what we really care about.
Right. We're looking at the shifting of the Pareto frontier between aggregate system throughput and per user generation speed, or TPS.
Yeah, at a moderate SLA service level agreement of 80 tokens per second per user on the V4 Flash engine, DSpark improves aggregate throughput by 51%.
But under a strict 120 TPS SLA, the baseline MTP1 degrades severely, while DSpark maintains a massive 661% nominal throughput advantage.
661%, that's insane.
Yeah. At matched system capacities, DSpark accelerates generation by 60% to 85% for V4 Flash and 57% to 78% for V4 Pro.
That is just night and day.
And what's fascinating here is how the verification budget adapts beautifully to load. At low concurrency, the scheduler allows 4 to 6 draft tokens per request. But as concurrency spikes to 200 requests, it dynamically restricts the budget down to 2 or 3 tokens to prevent resource contention.
That bouncer analogy really holds up. So what does this all mean? It basically proves we don't have to choose between parallel speed and autoregressive coherence.
No, we don't.
And we definitely don't have to blindly waste GPU cycles on doomed draft tokens.
And remember, the DeepSeek team has open-sourced the DSpark checkpoints and the DeepSpec algorithm repository, so you can literally implement this yourself.
Yeah, but there is one final limitation stated in the paper to think about. Even with perfect scheduling, DSpark still pays a fixed compute cost to generate the initial parallel block.
Right, you can't get those cycles back.
Exactly. Which leaves us pondering the next frontier difficulty-aware early exiting within the draft model itself. Oh, that's interesting. Yeah, if a query is inherently unpredictable, like highly creative writing, what if the draft model could autonomously refuse to draft at all? It would save that upfront compute entirely.
Wow. That would be the ultimate optimization. Well, that's definitely something to chew on. Thank you for joining us for this deep dive. We'll catch you next time on AI Paper Slop.